1.8, optimization with linear programming. This is new. Okay, this is new. First brand new lesson of the year. Here we go. Linear programming definition. It is a method for finding maximum or minimum values of a function over a given system of inequalities, with each inequality representing a constraint. All right? It's a method, linear programming is a method for finding maximum or minimum values of a function over a given system of inequalities, with each inequality representing a constraint. All righty? Now, the parts of up here you know what a system, wherever my finger is, there we go. You know what a system of inequalities is. Okay? We did that yesterday, right? That's what you guys just finished up. We did 2's. There was one on your homework that had how many? 3. All right, and y'all probably freaked out like, whoa, what do we do? Do it the exact same way. Okay? The reason I put that on there, I told 8th hour this, there's always a method to this crazy man's madness. All right? There's a reason why I put that 3 system on your worksheet, because you're going to do it today. Always a method to the crazy madness in here. It may be crazy madness, but there's a reason to it. All right? Your other definition is a feasible region. What a feasible region is, it is the vertices of the solution set. Okay? Now, if you look at these 2 graphs down here, if you look on your notes, they'll say the feasible region. That's just fancy talk for the overlap. Okay, that's all it is. It's just the overlap of the system of inequalities that you graph. And then your vertices, your vertices are your most important points today. Okay, the vertices where they intersect at. All right. Now we're going to deal with 2 types today. We're going to deal with bounded and unbounded. Okay, or at least hopefully we're going to get to both today. We'll definitely do bounded. Unbounded maybe tomorrow. We'll see how it goes. But bounded is the one on the left here. It's where you like graph it and then you close it up. Okay, like it's like all enclosed. It's bounded. It's grouped together. There's no openness to it. Unbounded, if you look at the picture, you can tell it goes down. The one on the screen goes down and down and down. The shading does forever and ever. Amen. Okay. Process to each one is kind of the exact same. There's one slight difference between unbounded and bounded, and we'll get to that when we get there. Okay. Any questions on that? That's basically all I got as far as intro stuff. Okay. Now, as far as how we actually do it. Is that how this goes? Straight to the next one? Okay. There's steps on here. But basically, the steps are right there in the directions, more or less. All right. Tells you what to do. Graph the system of inequalities. Name the coordinates of the vertices of the feasible region. Find the maximum and minimum values of the function for this region. All right, it's a lot. It's a lot. It's long, but it's not stuff you don't know how to do. Okay, I said it's brand new. It is. The process altogether is brand new. Everything we do today, you guys know how to do. Okay, you know how to do this. All right. So first up, graph the system of inequalities. So I'm color coordinating today. This one's going to be. Let's see here. I got a blue line. I got a green line, and I got a yellow line. And I'm going to graph that system. Okay? Now, for my line, first one here, this compound inequality. Book doesn't have compound inequalities in this year, so they assume you remember it, which I don't assume you do. This means y is between what 2 values? 3 and 6. 3 less than or equal to y, less than or equal to 6 together, right? All right, so you go to your y-axis, you go to 3, 1, 2, 3, right there. Okay, I'm going to draw me a little dot. Go up to 6, 4, 5, 6, right there. And then are these horizontal lines or vertical lines?
Horizontal.
Horizontal, okay. I messed up my colors already. One question and I'm messing up my colors. Can you believe this? 1, 2, 3. 4, 5, 6, and now blue line horizontal. there, and there, and there, and there. All right, so now your next line, y less than or equal to 3x plus 12. Okay, now, if you count these out, I'm pretty sure your graph only goes up to what? 10. Okay, so if you count them out, it only goes up to 10. This has been really bad today. I'm trying to get my finger to pop up here, but it ain't working. There we go. Okay, it goes up to 10. It still ain't really working that well. There we go. All right, but you start at 12. Okay, so you kind of have to grow up a little bit and understand what you're trying to do. If your y-intercept's at 12, that means the coordinate of it is 0, 12, right?
Yeah.
All right, so now you move according to your slope. It's a positive slope, but we got to go down onto our graph, so we need to go down 3 and right 1. Okay, or left 1, sorry.
Yeah.
Left 1, my bad. So we need to go from 0, 12, which is our y-intercept, down 3. So down 3 from 12 would be what?
9.
9,
Negative
left 1.
Negative 1, 9.
So 9, yeah, there you go. Negative 1. 9, right there. So that way you can get it onto your graph. Okay? Make sense? Occasionally you will have one that's like that, not too often. Alright, I do it on the first one just so you guys see it one time. But now go a couple more times. Down 3, right 1, or left 1, sorry. Down 3, left 1. 3, left 1. Okay. Another nice part about this, today they'll all be solid lines. So you don't have to worry too much about dash lines or anything like that. They'll all be solid. Okay, and then your third line you want to graph is y less than or equal to negative 2x plus 6. So 1, 2, 1, 2. So you start right there at 6. We're going to go down 2 and to the right 1 now. All right, now, these are inequalities. Okay, everybody got the graph, yes? These are inequalities, so there is still shading involved. Now, here's where this gets a little conceptually tougher / easier, okay, which sounds terrible, all right, but it's the truth. You would technically still test the same way you did last section, all right? Plug in 0, 0, shade towards truth. There's some shortcuts you can start to take, okay? For example, with this compound inequality right here, 3 less than or equal to y less than or equal to 6. This straight up says your y's need to be between 3 and 6.
It's not.
Okay? So that means the only parts of the lines that are going to be true are in between these two blue lines. Everybody see that? Because if you're going to have to have a y value between 3 and 6, it's got to be either 3, 4, 5, or any of the fractions in between the two. Make sense? Yes or no? Okay. Or also equal to, correct. Okay? Does that make sense?
Yeah.
Okay. Now, if you were to test, so our shading, quote unquote, has to fall between these two lines, the blue ones. And remember, you need overlap. Okay? Now, if you were to test the green line, you would get a true. If you were testing the yellow line, you would get a true. Right? 0 is less than or equal to 12. True. 0 is less than or equal to 6. True. So what do you shade? What's the overlap? It's a shade.
That middle trapezoid.
Very good. That middle trapezoid. All right, and I'm going to shade it in, I'm just going to do yellow. Okay. Everybody good? That shade is what is fancy speak here for your feasible region. All right? One thing before I move on. Notice I didn't shade this triangle up here. Okay, see that? It's not in between the two blue lines. It's above this blue line, so it doesn't get shaded. Okay, make sense? You have to be in between them. Yep. All right.
So you don't really need to even test that.
Not really, no, because it's always going to be in between them.
Right, so if you have something like that, you don't have to test that first one, just make sure
It's in between, correct. Okay. Now, you really don't care about anything else from here out except for the 4 vertices that touch shaded areas. Okay? You don't care about anything else besides those 4 dots. What you do care about with those 4 dots is the correct ordered pairs that they are. Okay? So this first one, let's see here. It looks like we're at what? -3, 3. Is that right? I've been terrible all day today at teaching things, so make sure I'm on the right track, all right? Looks like -2, 6 up here. Looks like 0, 6 right here. Pretty easy, count them out, right? What about this guy?
2, 3. 1,
2.5.
1.2, or 1.5.
1.5, 3?
Yeah.
Are you sure?
Yeah, 1.5, 3. That's definitely.
Are you sure?
I am
Would you
100% positive.
would you bet your grade on it?
Yes. I would. I would.
Would you would bet your grade that that is exactly hand drawn
I will bet
at 1.5?
15 extra credit points.
No.
That is
I would.
Martz, good answer. No. Good answer, kiddo. Good answer. No. Don't trust it. Here's why. These need to be exact. Okay? You need these to be exact. Now, here's some. Hang on, I'm getting there. We learned something. At some point in time, we learned something. If 2 lines intersect, it's a solution to a system, right? Remember that?
Yeah.
Okay? So we know the 2 lines. Whoops, I'm drawing on the wrong screen. There we go. This line is the line y equals what?
Y equals 3.
Y equals 3. The line that it's intersecting with is this yellow line, which is the line, not the inequality, but the line y equals what?
-2x plus 6.
-2x plus 6. That's a system of equations, right? So substitute 3 in for that y. And be sure. Okay? Don't guess. Be sure. So you go 3 equals -2x plus 6, which means -9. Right? Yeah.
No. Minus 6.
Oh, -3. Yeah, my bad. I've been terrible today, guys. I'm sorry.
Minus 6.
-6 equals -2x.
So it'd be 2 over 3.
Oh, gosh, still -3. God dang, I'm awful.
So it'd be 2 over 3.
So x would be 3 halves. 3 over 2. Right? -3 equals -2x.
Which is 1.5.
Which is 1.5. Yes, I know.
So I get it,
I
get it by 15.
No, you don't. No, you don't. Okay? But you have to be sure. All right? Because that could be thirds. All right? Remember, these are hand drawn. That could be hand drawn to a third. All right? So you're not 100%.
Well, since the intersecting line, the yellow one is by 2s.
But you still don't know that it's exactly half. Okay? You won't have a whole lot like that. Okay? All right?
Okay, good.
Not yet. We're not even to an answer yet. Okay? Everybody with me so far?
Yeah, I'm there.
Okay.
In spirit.
Good. That's where I want you in spirit. Now, next step. Take those 4 ordered pairs. Okay? Take those 4 ordered pairs. So we got -2, 6. We got -3, 3. We got 0, 6. And we got 3 halves, 3. Okay? Take those 4 ordered pairs. Now, Everybody looking? -2, -3, 0, and 3/2 are all what? X coordinates. Okay? 6, 3, 6, 3 are all what? Y coordinates. The only thing we haven't used yet is this function. F of x comma y equals 4x minus 2y.
Oh my goodness.
Okay?
This is so long.
So, I know. I've done this for 4 years. I know. I know. Oh, yeah. Oh, okay, yeah, complain. All right, great. Are we all done now? Fantastic. Moving along. So what you do next is you take all 4 coordinates, you plug the x's into x, plug the y's into y. Yes. All 4. Okay? 4 times -2 minus 2 times 6.
Why do you have to do that for all?
I'll tell you in a second. 4 -3 minus 2 times 3. 4 times 0 minus 2 times 6. 4 times 3/2 minus 2 times 3. Alrighty. 4 times -2, and then evaluate them, right? 4 times -2 is -8. 2 times 6 is 12. -8 minus 12 gives you, should be -20, I hope, if my math is right. Alright. 4 times -3, -12, minus 6 gives you -18. 4 times 0 is 0. 2 times 6 is 12, so 0 minus 12 gives you -12. 4 times 3/2 is 6. 2 times 3 is 6. 6 minus 6 is 0. Okay. All 4 evaluations. Now, last step. You want to find the max and the min values of the function for this region. Okay? This is the region. Your max or min values happen at your vertices, which is what you had over here, and then you plug them into this function. So your last step is to find the biggest and the smallest. So let's go with the biggest. What's the biggest number of that last column?
0.
0. Okay, so now you answer the question. I'm going to the bottom. You answer it this way. Come on. Your max is 0. And then you also tell me where it happens at, which is the coordinate 3/2, 3. Okay. Then you do the same thing for your minimum. I'm going to go on actually, oh shoot, where'd you go? There you go.
Oh no.
I'm actually going to go on the graph paper to answer that one. Okay, so max is 0 at 3/2, 3. What's my minimum?
Minimum is -20 at -2,6.
There you go. Okay. Your max is 0 at 3/2, 3. Your minimum is -20 at -2,6.
Holy.
There we go. Alright, so yellow line's my x's, green line's my y's, blue line's that diagonal, x plus 3. Alright, now, one like this is where you have to definitely make sure you do your testing. Alright, because it's not just one definite shape. Obviously, you're going to be between the greens and the yellows, so we're somewhere in this rectangle. Okay, but this blue line decides whether you're this little triangle or you're this shape over here. So that's what you got to test to see if you're going shading that blue line towards the origin or if you're shading it away from the origin. Okay, so that still all holds true. Plug in 0, 0, you get 0 is less than or equal to 3, which is?
True.
True. So blue line goes towards the origin, so that means you're this shape on the right side of it.
Is that 5 minutes?
Yeah. Okay. In the same way, anything the shading touches, any intercept that the shading touches, you need that coordinate off of. Alright, for this one also you have 4. Alright, everybody good? Okay, so over here it looks like we got what, 6, 1?
Yeah.
And then 6, 5. Over here it looks like what, 2, 5? And then negative 2, 1. Not always 4. Sometimes you could have one where you have 5 or something like that. So 4, 5, 3, somewhere in that vicinity you will usually be. Okay. You take your ordered pairs. So negative 2, 1, 6, 1, 2, 5, and 6, 5. In the same way, set up the table of you plugging them into the function. Negative 5 times negative 2 plus 2 times 1. Negative 5 times 6 plus 2 times 1. Negative 5 times 2 plus 2 times 5. Negative 5 times 6 plus 2 times 5. Okay. Do those evals. You get, let's see here, this is positive 10 plus another 2, so you get 12 on the first one, is that right? Let's see, negative 30 plus 2, so negative 28.
Yeah.
Negative 10 plus 10, so 0. And then negative 30 plus 10, so negative 20. Is that right? 4. Okay. And then same way, pick your biggest, pick your smallest, and write it out. So the max on this one is?
12.
Max?
12.
Negative 2, 1. And then your min?
Negative 28.
Negative 28. That's 6, 1.
Are the questions the same? How do we...
So I'm going to graph along with you guys. So this one, swing the 3x over, divide by 2. Right, since it's not slope-intercept form yet, so you should get y is greater than or equal to negative 3 halves x minus 6. Is that right? 3x over, divide 2, negative 3 halves x minus 6. Yeah. Okay. So go ahead and graph those 3 lines. All right. You'll have to do the trick that we talked about on the first problem with moving your slope according to your point, because 12 is off the graph a little bit on that first one there. Okay. Those are your lines graphed. Okay. Now, your vertices, where those 3 lines intersect, or the 2 lines intersect, honestly, are, let's see here, 1, 2, it's not negative 4, 0. Oh, that's a bad place to put that. Hold on. Negative 4, 0, and 0, what, negative 6? Yeah. Okay. Now, the question becomes, which way do you shade? And for that, you still do what you did on normal systems. You check every region. Okay, you do your 0, 0 check. Okay, so for your first one, when you plug in 0, 0, you get 0 greater than or equal to negative 12 for the blue line, which is true, which is helpful because that means we're going this way, okay, from the blue line. So it's either this one, or this one. Chances are it's going to be in between them. Just saying. Okay, chances are pretty high. All right, but check just in case. 0 less than or equal to 12. True. So green line towards origin. 0 greater than or equal to negative 6. True. Yellow line towards origin. So yellow, blue, and green are all towards the origin, which means you shade this center part right here. Okay. But notice how this one is unbounded. Right? There's no cap on the top of it. Let me change colors. There's no cap at the top. So this shading doesn't just stop here. The shading goes on and on and on that way. You do not. I'm being obnoxious right now. Okay? But I'm also making a point too. Alright? You only have to shade up to right there. Okay? Your process from here stays mostly the same. Okay? Mostly. Still take your two coordinates, -4, 0, 0, -6. Still plug them in. So 9 times -4, you don't have to write the -6 times 0 part. You know what that's going to end up being. Okay, same thing down here. So 0 times 9x is 0. So maybe write 0 minus 6 times -6. Right, for now, yeah, because you got 2 points that are shaded together, right? See the feasible region?
Yeah, you said for now.
For now, okay? Hang tight. All right, so right now you got -36 up here. Okay, and you got, what is this, positive 36? Right, 6 times -6 minus negative, yeah, positive 36. Okay. All right. Once you have that, I want everybody to flip back to the first slide. All right. Not the title slide. The first slide with stuff on it. Okay. Not the first problem. The one right after the title slide. All right. So one with the definitions on it. I want everybody to flip back to that real quick. Okay. Meg McKenzie, if I could read from yours, my dear. Thank you. I'm looking at the bottom right box where it's talking unbounded and bounded. Okay? Or the bottom boxes. When it says bounded, okay, it says bounded, the feasible region is enclosed or bounded by the constraints. The maximum or minimum value of the related function always occurs at a vertex of the feasible region. That's what we've been working on, the first two.
So this one has only one.
That's what I'm getting to. The feasible region, if you look to the box to the right with unbounded, feasible region is open and can go on forever. Hence my green all the way up my screen. This is unbounded. Unbounded regions have either a max or a min. They do not have both. Because this is unbounded and goes on forever and ever.
So it has a maximum, but it doesn't have a minimum.
We don't know which.
How come though?
Because you don't know if 36 is the max or if -36 is the min. We know one of them are false.
But can't we just look at the graph?
We don't know. Remember, there's no rhyme or reason. There's no real pattern. Just because this shades upwards does not mean that it has no max. Okay? So you have to try it. Now, the way you do that is you pick a point. You pick a point that you know is within the shaded region. Like, let's say,
0, 0.
Go big. Okay? Here you do have to go somewhat big.
8 and 8.
Okay? Let's go 0, 9. And plug it in. Okay? So I'm going to do this in blue. So do 0, 9. Alright, so 9 times 0 minus 6 times 9. 9 times 0 is 0. What's 6 times 9?
-54.
Nope, crap, sorry. 54, so you get negative 54. I'm down to the bottom, alright? For that. Okay? So, when you plugged in 0, 9, we got a value of negative 54, right here. Okay? Down here we had 36 and negative 36, right?
Yeah.
Okay? Plug in 0, 10, what do you get? Negative what? 60. Okay? You get negative 60, which is even smaller than negative 54, right?
Yeah.
Right? Yeah. Okay? If you keep going up and up and up and up and up and up, that shaded region, your numbers keep getting what?
Lower, lower, lower.
Smaller and smaller and smaller and smaller. Does that process ever stop? No. Which means you don't have a what?
Minimum.
You don't have a min.
So it's the opposite.
It depends on the function. Okay? So you... I'm sorry. You're a junior now. You have to think. Okay? So, you still write it out the same. Max 36 at 0, -6. And then you tell me no min. Okay. 10 years. Why can you not pick 0, 0 as your test point?
Because you need to do bigger numbers.
Why?
Because it makes the other numbers smaller.
There you go. That's kind of a roundabout answer, but I guess so. Okay. Why do you have to? Why can you not use 0, 0? It's just 0, Wags, which means it's between what?
Oh, you need to. It's in the shaded region.
Your answer is just not going to work.
Exactly. You won't determine nothing, right? If you plug in 0, 0 and you get 0, 0 is between 36 and -36. You didn't figure out which one is not your max/min. You didn't knock one out. You have to be able to go bigger or smaller than one of those numbers you find from your coordinates. Okay? So you do have to go a little ways away from your normal comfort zone of 0, 0, but you need to make sure that point is inside the feasible region at the same time. Okay?